So our first topic is going to be logic and sets. So we'll start with a basic definition of something called a proposition. So a proposition is a statement that is either true or false, but not both. So some examples, 2 is an even integer. That's a proposition because that's a true statement. The Cleveland Browns won the Super Bowl in 2010. Obviously, the Cleveland Browns did not win the Super Bowl in 2010, but it's still a proposition because it is false. A false statement, a true statement, those are both propositions as long as it's not neither or both. Third example, Earth is the only planet in the universe that contains life. Now this one's a little tricky. Is it a proposition? Well, it is either true or false, but we don't actually know what the truth value is. Earth is either the only planet in the universe that contains life, or it's not. We don't know, but that's still a proposition. Cool. A couple of quick non-examples, examples of things that are not propositions. The statement, "Where's the bathroom?" Also, the statement, I'll write down in a second. Some non-examples. So these are statements that are not propositions. First, where's the bathroom? Second, x plus 2 is greater than 6. So this is a mathematical statement similar to 2 is an even integer, but it's different in that 2 is an even integer is either true or false, in that case true. X plus 2 is greater than 6, it depends on x, right? So we can't say that this is a proposition. This is not a proposition. Okay. So the notation we'll use for propositions is usually P, Q, R. We could use any letter or any symbol, but we'll often use P, Q, and R. So for example, we could say P is the proposition, it is raining in Corvallis. We could write Q to denote the proposition, it is cold in Corvallis. So in mathematics, usually we start by studying some kind of objects. In this case, we're studying proposition. This subject is called propositional logic. And the next thing we do after we have some objects to study is we figure out how to combine them in different ways to create new objects. So the first ways that we'll combine propositions to create new propositions is called conjunction and disjunction, or in simpler terms, and or. The notation we use for and, which is called conjunction, is the following. So sort of a sharp pointy hat means and a V means or. So continuing with our examples P and Q here, it is raining in Corvallis and it is cold in Corvallis. If we write P and Q with this notation, this means it is raining and cold in Corvallis. Likewise, P or Q means it is raining or cold in Corvallis. Now, it's important here to note that or, when we talk about disjunction or, this is a mathematical type of or, and it's not the same or necessarily that we use in common English language. Now, in particular, in English, the word or can mean two different things. It could either mean one or the other or both are all possible. On the other hand, it could mean what we call exclusive or, which means either one or the other, but not both is possible. So in mathematics, this V symbol, disjunction, mathematical or, we always use to mean inclusive or. And we have a different symbol that we'll use for exclusive or. So the V means inclusive, or P or Q means P, Q, or both. And a sum with a circle around it in your textbook will denote exclusive or. Which is P, Q, but not both. A common example of exclusive or in common English would be if you're ordering at a restaurant, for example, and they say an entree comes with soup or salad. That doesn't mean you can have both soup or salad. You have to choose only one. Okay. So we said before that being a proposition means that you have a truth value. It's either true or false, but not both. Right? So that means that if these are propositions, if P and Q or P or Q are propositions, we're going to ignore the exclusive or for now. I just wanted to highlight the difference. Then we want to know, well, what are the truth values of these new propositions that we created? So when is P and Q and P or Q true or false? Well, it should depend on whether P and Q individually are true or false. We can catalog this in a table. So P and Q should only be true if both P and Q are individually true. P or Q should be true if either P or Q or both are individually true. So we'll catalog this in a truth table. We'll call this a definition because this is defining the truth value for P and Q or Q depending on the truth values of P and Q individually. So P can either be true or false, Q can either be true or false, and so there's 4 different pairs, true-false pairs that the P and Q can have. So here we have P and Q are both true, P is true and Q is false, P is false and Q is true, or P and Q are both false. The only instance that yields a true conjunction, P and Q, is the first one. When P and Q are both true, P and Q is true. If either one is false, which is all the remaining cases, then the conjunction is false. P or Q is different, sort of opposite. Pause for a second and see if you can figure out what the truth table should be for P or Q. Okay, let's see if you guessed right. So we know that P or Q should be true when either P or Q are true. It doesn't matter if both are true. So that occurs in the first 3 of the 4 cases. The only situation that would mean P or Q is false is if both P and Q are false, and that happens in the 4th case here. Okay. So let's review a couple quick examples of the truth value of a and or an or statement. So our first proposition P will be the statement, a decade spans 10 years. Our proposition Q will be the statement, a millennium spans 100 years. So first question, is P and Q true or false? And our second question is P or Q true or false? So pause here for a second and see if you can use the truth tables to figure out the answers to these questions. Okay, well, P and Q is true if both P and Q are individually true. The statement P, a decade spans 10 years, this is true. This proposition Q, a millennium spans 100 years, is false. A millennium spans 1,000 years. So that means we have true, and false. Together, that is false. P or Q, on the other hand, only requires one of the two propositions to be true. Since a decade does span 10 years, it doesn't matter whether Q is true or false. We have true. Cool. So far we've learned two ways to take propositions and create new propositions. The next way, we can do it with just one, and it's called negation. So the negation of a proposition is just, we call it not P. So the negation of a proposition P, we denote it by a special symbol that we read as not. The symbol looks like this. And its truth value is just the opposite of the truth value of P. So for example, if P is true, not P is false, and if P is false, not P is true, which we can denote in a very small truth table. Since P can only either be true or false, this will be a 2 by 2 table. Like so. For a quick example, proposition P could say Paris is the capital of England. Then proposition not P would say Paris is not the capital of England. And of course, one of these propositions is true and the other is false. In this case, P is false, Paris is not the capital of England, so not P is true. Okay. So the next way we can construct new propositions is called a conditional proposition. And this is one of the absolutely most important types of propositions that you will encounter, and is the following form. So a conditional proposition is any proposition of the form if P, proposition 1, comma, then Q, proposition 2. So the notation we use for a conditional proposition is P arrow Q. And we can either read this as if P then Q or P implies Q. The proposition P in this position we call the hypothesis. Proposition Q we call the conclusion. And the arrow we call the implication arrow. So a particular example. Proposition P, I get paid today. Proposition Q, I buy an ice cream sandwich. What does the conditional proposition P implies Q say? This says, if I get paid today, then I will buy an ice cream sandwich. So, like our previous examples of combining propositions to make new propositions, the truth value of a conditional proposition will depend on the individual truth values of P and Q. In particular, the truth table, which defines the truth values, is exactly the following. So we have 4 pairs of values, true, 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 false, false, true, and false, false for P and Q. We define the truth value of P implies Q to be true if P and Q are both true, to be false if P is true and Q is false. This makes sense because the statement if P then Q, you would expect that whenever P is true, Q must follow as well and be true. So if Q is false and P is true, that's a false statement. What maybe isn't natural is that the following false true and false false also give a true result. But this makes sense if we think about it. Because this is a conditional statement, it means that all it's saying is if P, then Q. That means if we can't say that P is true, it doesn't matter what the conclusion is, that the whole statement itself is true. So for example, in this particular example, P is the proposition I get paid today, Q is the proposition I buy an ice cream sandwich. The statement, if I get paid today, then I will buy an ice cream sandwich, is true if I don't get paid today. Because it's not claiming anything about that case. It's a little weird, but that's the way it works. In these two situations, where the statement P implies Q is true because the hypothesis P is false, we say that it's a vacuously true statement. That might help you remember as well. Okay, so one last example for this section. So let's say we don't know exactly what the statements P, Q, and R are, but we do know their truth values. So let's suppose P, Q, R are propositions such that P is true, Q is false, and R is true. So the question is to determine the truth value of the following proposition. So the proposition we want to determine the truth value of is P or Q implies not R. Okay. So pause for a sec and see if you can figure out the right answer. All right. So let's see if you got the right answer. So we know that in order to figure out this implication, we need to know the truth value of the hypothesis and the truth value of the conclusion. Okay. And what I didn't explain yet, but I probably should have, is that there's an order of operations to these operations on propositions, just like there's an order of operations that you learn in grade school for the multiplication, addition, parentheses, exponentiation operations. So in grade school, you probably learned, please excuse my dear Aunt Sally. Right, for parentheses, exponentiation, multiplication and division, and addition and subtraction. Well, just to help us, I invented another mnemonic device for this situation, which is please not another Oreo, ick. So here this corresponds to parentheses, negation, and, or, and an implication. So this is the order in which we should understand these operations. If we apply this to this problem, then without needing the parentheses here, we know the implication is the last thing we should do. The first thing we should do is deal with the negation, right? We know that R is true, that's given, so we know that not R is false. Next, we should deal with the or. We know that P is true and Q is false, so P or Q is true due to our truth table previously. Now we can determine whether the implication, the last thing we do, is true or false. True implies false is false. Okay. Perhaps one thing that will be helpful is to see a truth table for a little bit of a larger case. So I was going to finish with this example, and I'll just do one more because I think it might be helpful to see. So this example is to determine a full truth table for a proposition that involves three different propositions, P, Q, and R. So in particular, we're going to try to figure out the truth or falsity of not P or Q and R, depending on the individual truth values of P, Q, and R. Now, when we had negation, that only involved P, so we had a very easy truth table, 2 by 2, because P had two choices. When we had truth tables involving P and Q, there were 4 possibilities for the truth values of P and Q combined, because there's 2 for P and there's 2 for Q, so together that makes 4. In this case, there's going to be 8 total possibilities. And you'll see more why that's true when we get to the counting section. So, just to give a table indicating the possibilities for P, Q, and R, we'll already need 8 rows. We can have true, 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 false, true, false, true, true, false, false, true. This is the 2 version with all trues for R, and then we could do the same thing with all falses for R. True, true, false, true, false, 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 true, false, or false, false, false. Not P is going to be the opposite of the P column, so this will just be false, false, true, true, false, false, true, true. And now, and Q and R. We know Q and R is only true if both Q and R individually are true. So we get a true, false, true, false, 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 false. Now we can combine not P together with Q and R in an OR. It's going to be true if either one is true. Which gives us a true, false, true, true, false, false, true, true. I have something different written, so I'm going to double check. I did my table in a different order, so we're fine. Alright, so that's it for lesson 1.